Okay, so welcome everybody to our session in the Mel Theory channel at the Cohere for AI Open Science community. Today we have Dr. Charles Martin on this work of his, of WeightWatcher and the theory behind it. So a small description of the bio of Charles Martin. He worked before in theoretical chemistry, and then he did a lot of AI, and he has been applying it to many companies. Among them, there is Walmart, eBay, and many others, over 15 years. And he has been he has published a couple of theoretical papers that are that have had quite a lot of impact. And today he will be talking about some of this theory. So yeah, like you can start, Charles.
Okay, great. Thanks for having me. Today, I'm going to tell you today about something called the WeightWatcher project. And this is a project to develop a theory to provide data-free diagnostics for deep learning. So, as I said, I did my PhD in theoretical chemistry at the University of Chicago. You might know my more famous group mate, John Jumper, who just won the Nobel Prize for AlphaFold. Then I was an NSF fellow in theoretical chemistry at Champaign-Urbana. You may know another famous classmate of mine, Jürgen Schmidhuber. So at that time, I was doing theoretical physics and chemistry for AI. This is way back in the 90s. And about 10 years ago, this stuff started heating up again. So I sat down and started thinking about how I can apply some of the things I've done in theory and in some of my industry work at various startups and on Wall Street to figure out how to build a theory and a tool which people could use to help them to train and monitor their own models. This has led to an open source tool called WeightWatcher. WeightWatcher is an open source diagnostic tool. It's based on a number of theoretical papers that I've published sort of informally with a friend at UC Berkeley. Into why deep learning works. Right now, the tool actually, it says 115. It actually has 107. I think we have 185,000 downloads right now and over 1,000 stars. And it's an Apache 2 licensed tool. So today I'm going to talk to you about the tool and what you can do with it, and then I'll talk to you about the theory behind it. And again, coming from a physics background, this is a tool which is really based in ideas from theoretical physics, which may be somewhat different than the kind of things you might see in statistical learning theory or computer science. The basic idea of the tool is that it analyzes the weights of a weight matrix, hence the term WeightWatcher. So you'll take if you have a neural network, you have these layers. It's like the green, maybe the data. You feed, this green is the data. You feed the data into a layer. The layer has a weight matrix associated. It's usually some rectangular matrix. You perform SVD, spectral composition, spectral analysis on the weight matrix, and you can obtain the singular values, which you can turn into eigenvalues, and you plot a histogram. And it turns out that the structure of this histogram actually tells you an enormous amount of information about the generalization properties of the network. And in particular, what you find is that when you start training a neural network and you initialize the model, you're starting with a random matrix. So if you compute the eigenvalue spectrum of each of the weight matrices and you plot it, it will look like a random matrix. They can be fit to something called random matrix theory, which is what we see in this plot on the left. The red line being the fit from the Marchenko-Pasteur random matrix theory. As you train a model, information will begin to pull out of the random matrix. You'll see sort of larger eigenvalues. These are spikes. This is just PTA. Everybody knows PCA or SVD. It's not particularly very interesting. But it turns out that as models start to converge, the spectral density becomes power law, and you can plot. If you were to plot if you were to fit this spectral density row of the empirical spectral density for each eigenvalue lambda, you would find that it can be fit very well to a power law of minus alpha, where alpha is the power law exponent. This turns out to be something very special and something we know in theoretical physics, which has led us to develop an entire theory around this simple idea.
Perhaps you can answer the following question: are there bounds for alpha?
Yeah, so we'll get to that. You'll
Okay.
see, see as we go down. It turns out, yes, there's a whole theory of universality classes for these classes of distributions, which come from the theoretical physics literature, which aren't well known in even in the statistics literature or mathematical literature. And I'll talk a little about where those come from and how you can learn from that. Where am I going? And that's described in a series of papers. For example, I have a paper I wrote in 2021. Actually, the work was done in 2018, so this work's very old by now. Implicit self-regularization, deep neural networks, evidence from random matrix theory and implications for learning. In this paper, I go through the theoretical physics literature and show that there are different universality classes of random matrix theory, and you can use these universality classes to build a theoretical phenomenology to understand better how the individual layers in the network converge. Then we also have a paper in Nature Communications where we did the first large-scale meta-analysis of open source models. Back when I started this work in 2018, there were only 50 open source models available: VGG, ResNet, DenseNet, things like this. Now, of course, there's probably over 1 million open source models available on Hugging Face. So this work was started very, very early before Hugging Face existed. And of course, today we can apply the theory to very, very large neural networks like Llama and Falcon and Mistral, and you'll see that. I also have a new paper that's coming out. Hopefully it's over 120 pages long. It's a deep theoretical physics dive into the theory called Semi-Empirical Theory of Learning. I'm happy to share a draft with anyone who wants to read it. Whether it ever gets published, we'll see. But it's basically done. But you know, it takes a little while to push things over the mountain to get it over. So that's where we are. But I'm much more interested in giving people a tool. So it's much more important to me that I give you a tool with the theory in it so you can apply the theory. And I'm happy to share and answer any questions about it. So let me explain to you what the theory is doing for you. And the idea is that when you think about how a neural network converges, most people think about the loss. They'll look at the loss, look at the Jacobian, the Hessian, things like that. But the individual layers have to converge as well. You're starting off when you begin training a model, and you were, for example, if you were to look at this x-axis being something like the number of epochs that you run the model, it's not labeled, it's epochs, and this is some measure of the loss, some measure of something like the loss. You might find that as you train, you start off with a random matrix, and some layers just always look random. They just never seem to learn any information, or they learn some information, but it's so weak. There's so little information in the layer that it's very hard to distinguish what's going on using spectral analysis. And that's many layers will look underfit. And there's a quality metric, the WeightWatcher HGSR theory layer quality metric alpha. Alpha has a range. And so it turns out that the theory says that if the range is like 6 and above, then the matrix looks fairly random. You can't see any structure in it using the theory. Doesn't mean it hasn't learned anything, but it's just so weakly trained that we say that it's underfit. There's also alpha can be very small. If alpha turns out to be less than 2, in the lower bound of the estimator is about 1.5, the layers tend to look overfit. So the layers may be overfit, it may exhibit rank collapse. There's a large number of zero eigenvalues. So the theory predicts this. And the theory also predicts that there is an ideal state of every layer. So in an ideal network, every layer would obtain an alpha of 2. And that's the theoretical prediction. And part of what we're trying to do is to test the theory empirically to see how well that prediction holds. Does it hold for every layer? Does it only hold for some layers? Where should it hold? Where does it not hold? And how can you take advantage of it? And this is the point of this project. Just to clarify what's going on, it's really conceptually extremely simple, and if it's going to make a useful theory, it has to be very simple so engineers can use it. The idea is I analyze the tail of the empirical spectral density. It is a histogram. This means histogram of the eigenvalues of the layer weight matrix. So, for example, here in VGG 16, an ancient model by now, you would take the last layer, which is a FC3. If it's just a simple linear layer, I compute its eigenvalue spectrum and I plot it on a log scale. And when I do that, I can fit that plot to a straight line. When the slope of that line corresponds to the quality of the layer. And if the layer is not doing very well, you might find a slope of 4. So you find alpha's 4, and that's okay, but it's not great. In the ideal case, you find that alpha equals 2. You get a really clean fit. You see this very smooth fit. It's very clean. There's a little noise in the tail, but you're fitting the tail. This is the basic idea of the theory. It turns out that when you do this, there's actually some very deep theoretical physics here showing that not only in many cases the theory says phenomenologically that it's just through observations, and very generous application of random matrix theory. You see, when alpha equals 2, you get an ideal state of the layer. And these plots, the red is sort of the theoretical fit. So it's an okay fit. It turns out there's also a condition you can derive, which I have derived now, from first principles to some level of rigor, what we might call a physics or a theoretical chemistry level of rigor, where you can show that the sum of the eigenvalues in the tail, that is all the eigenvalues to the right of this red line, this is the tail, the large eigenvalues, the sum, the log of the sum, we call this the trace log of the eigenvalue should equal 0. And so if you run the tool and you set a condition on the tool to give you these plots, it will try to fit the ideal power law, and it will give you this red line telling you the start of the tail and the exponent. And it will give you this purple line telling you the start of the tail given this volume preserving or scale invariant transformation. And when these red and purple lines overlap very, very closely, the theory is working perfectly. So this is a very good example. So again, these are two independent theories. They're not related. They're related to each other sort of empirically. Theoretically, there's some very, very deep stuff going on here. In physics, we would say we believe that the 2 is a critical exponent associated with this condition, which we can talk about a little later, is associated with or analogous to taking one step of the Wilson exact renormalization group. So it turns out this empirically holds really well. And I'll give you some examples of things that are confusing in the machine learning and theoretical AI literature, which are very straightforward to explain with this theory. So for example, double descent. Double descent is something people have talked about for a very long time recently. They've talked about recently, but in fact, it dates back to the late 80s. It was discovered in the theoretical physics literature, a double descent model. And the model was simply, I want to train a linear regression on a problem to classify binary labels on a problem which is widely overparameterized, like a system where you have 2 to the n features, and I want to classify it within examples. And it turns out that this is an old problem from theoretical physics, and I'm happy. I have a blog post where I explain this problem, and I have a notebook where you can run it, and you check out. You can check and run out. So I'm happy to share that with you. But the idea is that if you're in the overparameterized regime and you try to compute the test, you try to fit this model in overparameterized regime, it turns out the error is quite high, but you get the error down to about this y-axis is, if you plot the error on this y-axis, the error is minimized at this point. So you have this orange curve. These dots represent the overparameterized regime. It turns out the minimum of this curve corresponds to alpha equals 2. And the trace law condition holds. So these 2 independent conditions hold. The best test accuracy in the overparameterized regime at PL alpha equals 2, the start of the power law tail, and the volume preserved transformation hold. And and you also see other points when you get to these high error, you'll see that the model is overfit. So again, I have a blog post that explains all this. It's very straightforward. This, of course, was all described in before my theory came out. This was all described in the theoretical physics literature in the early 90s. I'm happy to share some papers on that. So this has always been well understood in physics. Another question people ask me is, can you use the theory to regularize a layer? Everybody wants a regularizer for their models. And the answer is yes, of course you can use a theory to regularize it. But in theory and practice, practice and theory are the same. And in practice, they're different. So, when you try to apply the theory, it's very technical. There are some engineering things you have to do to get the theory to work correctly. And if you don't do it right, you screw it up. But in particular, you can do it now because PyTorch has a differentiable SVD. So you can run SVD on each individual layer and try to fit the power law. But it's tricky. Can you use it for better initialization? Let me get to that in a minute. When using it as a regularizer, it's tricky. So let's just say it's tricky to apply it as a regularizer. Someone asked me, can you use it for better initialization? I have no idea. The theory is about the theory of WeightWatcher is how do you drive a model to each individual layer to its ideal point. So it doesn't matter where you start. Wherever you start is where you start. It will drive you to that point. There are other theories trying to converge faster by giving you the initialization, but the theory is so close to the critical point, to the fixed point, that we don't have a good description outside of that point. So we know how, once you get close there, we can accelerate you to the bottom. We can get you to the bottom of the curve. But when you're first starting off, that's a different problem for us. There are some theories that help you, but for what variance control, things like this. Which in physics would be like a temperature control, but that's not a problem I'm addressing. Other problems we can address though, grokking. One of the things people thought, what is grokking? Well, grokking is this idea. If I take a model and I train it on a very small number of examples, it will you train. So this example, I have a very, very large number of epochs on the x-axis. So this is, I think, even a log scale. So some huge number of epochs, and then the accuracy is on the y scale. And you see, if you try, I think this is a 3-layer multi-layer perceptron trained on NNist with like 1,000 training examples. This is one of the fellows on our Discord channel did this to show the theory. And if you train this for a while, all of a sudden the training accuracy will jump to 1. So you fit the data, the training data perfectly. But the test, you don't basically get any test accuracy whatsoever. This is the green is the test accuracy. Then at some point after training for a very, very long period of time, the test accuracy will jump and you get some reasonable prediction of the test accuracy. It's not great. It's like, 85% or something, but it's not random, right? It actually does something. This is grokking. So if you monitor the layer alpha, what you'll find, this is the different layers in the model. FC1, blue is FC1. I'm sorry about the notation. FC1, FC2, FC3. Well, we can take a look at, for example, at FC2, which is the orange. You'll see that the alpha is around 5 or 6, which is not great. It's got a little bit of information, and the FC3 is around 5. So again, the alpha is fairly large. It has a little bit of information. As the training accuracy increases, all of a sudden the alpha goes up, which is kind of interesting. The alpha jumps. The first layer, alpha is very large. So again, you really can't see anything. You don't see any structure in the model. It's learned, but you try to analyze it with random matrix theory, you don't see anything. Then all of a sudden, when the grokking kicks in, bam, you see a phase transition. The FC2, this orange layer starts dropping down. The alpha drops to 2. The first layer all of a sudden starts fluctuating. Its alpha jumps up, and then it also drops down to 2, and around 2 or 3, something like that. And the third layer does the same thing. It's just it only has 10 eigenvalues, so the estimator has a huge amount of noise in it. But basically, you can see using the theory, using WeightWatcher, you can see this phase transition kick in, which is associated with grokking. So you see this in the theory. Not particularly surprising. It's a phase transition. We see phase transitions in physics all the time. This is what's going
on. Perhaps I can interrupt you here. Can you go to the previous slide?
Yeah, sure.
Yeah. So as far as I understand it, this connection between the grokking starting happening and the phase transition is kind of empirical, right? You observe that at the same time that the alpha increases in this high jump, you see a high.
Yeah, it's an empirical observation, right?
Right, but like there is no, at least the theory doesn't explain yet why, right?
So in this theory that I'm developing, this is actually a good question. I'm not trying to provide explanations. We're not trying to provide an explanation or a mechanism for what's going on. One of the things about statistical mechanics and renormalization group and complexity theory is that you can see universal patterns and you can make predictions without having to actually understand the underlying mechanism. That doesn't mean there's not some but so I actually make no attempt whatsoever to provide any mechanism for what's going on. The goal of this theory is to show that there are these universal signatures of emergence, this phase behavior, which emerges when a model starts getting close to convergence, and your ability to detect this and to use it to accelerate convergence. But I have no, one of the other guys in the channel is trying to use, for example, he's looking into this and he's trying to look at some of the theories that Anthropic have done, like circuit, trying to do circuit analysis. But at this point, we're not trying to provide any kind of mechanism of any kind. This is purely observational and universal theories.
Right. Good.
So that's all.
Yeah, there is another question. Mayank, go ahead.
Yep. Does this mechanism works for the mixture of experts or like VLMs in particular, the language models?
That's a good question. I'll get to that because I am going to look at some of the LLMs, and the quick answer to that is I'm not sure. In fact, I'll show you now. So let's jump down to Llama. Okay. So if we look at Llama versus Falcon, we can look at the alphas for Llama. You can plot a histogram of it. This is now alpha for every layer, right? And you'll see that when you look at a model like Llama, a large number of the alphas lie between 2 and 4. So we call this the safe zone. So between 2 and 4, you see that the alphas are there. And then there are a lot of alphas which are larger than 6. So you see a large number of alphas which appear to be underfit. This is common for many, many LLMs. The only one I haven't really seen is the original Falcon. didn't seem to show this. And then when they went from Falcon 1 to Falcon 2, you started seeing the same thing. So many models show this. It turns out that different models have different numbers of overfit layers. Llama has the most. Then Llama has like, this is like 25%. Llama, Quinn, I think, has 20%. DeepSeek has 10%. Okay. So it does seem as the models are getting better that you're seeing less of these. What are these associated with? Okay. So if you look inside an LLM and you ask what's going on in the individual layers, we look at each of the layer types, V, up, Q, K, etc. The K and Q layers appear to have near perfect correlation structure. So this is this dotted line here, and red is 2. So this is 2, 3, 4. It's probably 3.5 here, right? About halfway through between 2 and 5. And you can see that the theory is described like we look at for Q. This is the purple line. You can see 2, 3, 2, 2. It's around 2.5, 3. So it's in this range, right? This is this peak here around 2.5. This is where the K and the Q layers are. If you look at V, for example, though, the V layer, it's all over the place. Right? If you measure, it almost looks like a random matrix. We can't tell what's going on. V is just very wild. It doesn't appear to capture a lot of correlations. And so I'm trying to dig into that. Now the question about mixture of experts, when you look at mixture of experts, what you find is that you see the same structure. You'll see that the K and Q layers show this structure. I don't have the picture, but I was saying in words. And what happens is there are these gates, like in the mixture of experts, there's these other layers that sort of route, and they appear to be more random. And the explanation for this, like I can sort of give you an analogy, is the theory I have, if you go through and look at the deep theory, uses some techniques from theoretical physics, which are also used in wireless communications. And there are models in wireless communications of channels communicating, like in a city where the cell phone towers are communicating. And sometimes you'll see the correlation structure shows certain cell towers are capturing all the information. And in other models, you'll see it's very dispersed. So we're seeing in the mixture of expert models that certain layers appear to be very dispersed, and they're like the routing layers, but the internal layers retain this correlation structure. Does that answer the question?
Yeah, that does. Thanks.
Yeah. So other things you can show, the theory, you can do things like you can detect overfitting. So there are cases where here's an example where we run a 3-layer multi-layer perceptron on Minst, and we train it very carefully. And this isn't like super high accuracy. You can even get this thing to very, very high accuracy. But here, you basically increase the learning rate. This is described in the new paper. So I run like FC1, FC2, here's FC1, FC2 for a 3-layer multi-layer perceptron on Minst, and you train it as you increase the learning rate. This is the error goes down, the error goes down, the error goes down. All of a sudden, the error will jump. Okay. So if you get the learning rate too high, you can force Minst to overfit. Likewise, with layer 2, and what you do is here is the y-axis, the error, the x-axis is alpha. And you'll see that in the state where as soon as the layer starts to overfit, the alpha will go all the way to 2, and then it drops below 2. And this happens both for FC1 and FC2, but FC2 has the error bars are much larger. Okay, so FC1, the error bar is very small. FC2, the error bar on alpha is very large. Basically run the experiment 10 times and measure the error bar. But what you see is that the test error will jump. The test error goes up, the alpha drops below 2. This is predicted by the theory. This is associated with a rank 1 perturbation in the layer weight matrix. I call this a correlation trap. So the idea is that if I take the layer matrix and I randomize it element-wise, and I compute its eigenvalues, it should satisfy random matrix theory. So green is a plot on a log linear scale. There's a log linear scale. It's easy to see what's going on log linear. The green is a correlated system. Green is a real system. It's correlated. It's power law, and it has this sort of funky shape on a log scale. Red is Marchenko-Pasteur theory. I took the original random matrix. I randomized it element-wise. When you randomize a matrix element-wise, it obviously is now a random matrix, and it should satisfy random matrix theory. So it does. However, in the large learning rate, what you see is that when you randomize the matrix element-wise, you see that there's a large rank 1 perturbation. There's some weird large element or combination of elements causing one of the eigenvalues to become very, very large. So we call this a correlation trap. This large rank 1 perturbation in the randomized matrix is associated with this error, this sudden increase in error. We're not sure yet, like mechanistically, like what's going on inside the model, where is it overfitting? But we certainly know that in many cases we can see that the formation of these weird rank 1 perturbations corresponds to some sort of overfitting. That's one of the theories, one of the conjectures of the theory, one of the predictions of the theory that we're trying to flush out. Other things, you can apply the theory to the updates of an LLM. So rather than apply to the full LLM, let's say you want to fine tune an LLM, instruction fine tuning, reinforcement learning, fine tuning, that kind of thing, where you're changing, not LoRa, where LoRa is like you're changing like eight eigenvectors. It's too small. But if you're doing like a full fine tuning, large scale instruction fine tuning, something like this on a base model, you can apply the theory directly to the update. So, for example, here's Falcon, series of Falcon models. The full model is like, say Falcon, this bright green is Falcon 310B instruct. I take the model, I subtract off the base Falcon 310B. So for every layer, I subtract off the base model. And WeightWatcher will do this for you if you specify it. And I have a SaaS product also, which I built, sort of trying to offer as a product to people, and it will do it for you on the cloud and handles all this. But it will do all this for you. And you can apply the theory. And what we see is and there's a theoretical reason why you can do this when you go into the theory. It has to do with treating these two objects as two different random matrices, so they're uncorrelated matrices. You add them, it turns out you can apply the theory in this way. There's a theoretical justification for this, which we can go into if you want. But the idea is that if you plot the alphas for just the instruct component, you'll see that they all lie in the safe range between 2 and 6. You can do this for Llama, you can do it for Mistral, you can do it for Qwen. Almost every model, except for there are some exceptions. Every theory has exceptions. I'm not sure why the exceptions are there, but for a large part of the instruction fine-tuned models that we've seen on Hugging Face, the teal green here is the base model. The purple is the instruct component. Once again, I take the full model and I subtract off the base, and I just get the instruct component. And the instruct component is in purple, and you can see that for Llama, for Mistral, and for Qwen, all the instruct components fall between the 2 and 4, 2 and 6, even 2 and 4 was even better safe range, which seems to be that when whatever these big groups are doing to do instruction fine tuning, it seems to be working fairly well. We've had some cases in other where maybe you do mixture models or other things. We've worked with teams to try to figure out when does it fail. So we had one group, for example, in Poland that was trying to create a Polish language model, and they did exactly what was done in Solar, like this model called Solar 10B, and they just kept getting weird results. And so this is what you can use the tool for. And generally you find that this is a plot of the x-axis is the alpha for the base model, y-axis is the alpha for the instruct component, and there is generally a weak correlation. If the base model has a lot of large alphas, you can see large alphas in the instruct component, larger. So the base model might have an alpha of 15, just basically a random matrix, but the instruct component could be 4.5. So it's not a perfect correlation. It's very weak. Obviously there are even cases where it doesn't even matter. They're like, this is a weird straight line, and this is something we want to dig into more. But generally speaking, the models, having sort of models that have underfit layers, you can still instruct fine tune them, and they'll get into this nice range. It's almost says that if the model's too well fine tuned, too well trained, if the base model's too well trained, it might actually be harder to fine tune it, because it turns out the alphas have to be really, really small, and you have to capture a lot of correlations, and you can even overfit. So that's one of the predictions of the theory. And there is some evidence showing that models that are I can send a paper on this if you want. I have a blog post I have a Twitter post on it where models that are really, really well fit turn out to be a little harder to fine tune. But that's not necessarily bad. So there's some different things we've done to sort of interpret what's going on when you have overfitting. Overfitting could be good. So for example, we take a look at the segment anything models. Segment VIT base, AM2 higher image. So you look at the segment any2 models, turns out they have a huge number of layers where alpha is less than 2. And this is huge, has an unusually large number of layers. And this theory would say, these layers tend to be overfit. Okay, well, if you look at the actual layer, you look at where they are, we call this a correlation flow plot. On the x-axis, you have the layer ID. which is basically how close is the layer to the data. So 0 means you're very close to the data. 300 means you're close to the labels. Why? The right side is close to the labels. Different, obviously different models have different sizes. But you see the same trend with both the segment anything models. They have a lot of layers that appear to be overfit, which are very, very close to the data, which, are really very primitive things. And so the idea being that in order to, and the segment anything models are really good for zero-shot learning. So the idea, the interpretation, and again, we don't have the mechanism, so this is just a prediction, which has not been verified. But the prediction, the interpretation of the theory is that the segment anything models are memorizing these very primitive features of vision, which are shared across all images. And so it can do zero-shot learning on similar images because it has memorized some very, very abstract features. Maybe I call them primitive features. There's some argument, I would call it abstract. Some people say the features out here are abstract, but it memorizes primitive things like lines and simple shapes in the images that it can then use to do zero-shot learning. Here's a counterexample of Llama. The Llama models, Llama Guard models, Llama Guard 1B and 3, 1B and 8B. These Llama Guard models, here's a case where you see overfitting is bad. So in this case, you see the same thing. There's a huge number of layers that are overfit, but now the layers that are overfit, for example, we look at Llama Guard 3AB, the purple teal, you see a huge number of layers now are closer to the labels, meaning that you've really now tried the guard models, and the interpretation here, again, it's a prediction. The interpretation here is that you're overfitting to the training examples and the abstract parts of the training examples to try to prevent the model from asking bad questions. You're not allowed to ask those questions, so it tries to prevent you from asking them. And as a result, the model becomes a little brittle and sometimes does funny things. But this is the interpretation of the theory. An interesting result we discovered a year and a half ago, maybe it's been 2 years now, I think, that if you compute the average alpha for a base model and you plot it versus the truthful QA metric, it turns out the better a model is trained, according to the theory, the better it is at lying to you. So it will make stuff up. It's better at making stuff up. And that's sort of an interesting result. I even have a TED talk on this. It was so surprising. There's a very weak correlation. It's not a huge R squared, and there's some outliers, but it's sort of this general idea that the better a model is, the better it is sort of BSing you. And there's been some research now, people doing things like adding I don't know tokens to models and trying to resolve this. But this is a very curious result that I want to point out. Another example that happens, just to understand some of the complexity of what's going on here, I sort of present this as you take a spectral density, you fit it to a straight line, you get some information. The fits are a little more tricky. There's a theory in theoretical physics called Dragon Kings, which has to do with extreme outliers relating to systems that are governed by power law, in particular systems that are governed by self-organized criticality and sort of phase behavior, that you can't see very, very large outliers. So you can do it. You can see, like here, you plot on a linear scale, Linland scale, some random layer from a neural network, and you see it has this nice power law structure. But there are these, if you try to fit it to a power law, you see these structural outliers. And this sort of confused some of the students at UC Berkeley when they were trying to do this, and were convinced there were bugs in the code or something. No, this is known. And by the way, WeightWatcher will handle this for you. So if you try to write the tool yourself, part of the tool is that it handles this kind of things. These structural outliers are predicted by there's a physicist called Dieter Sornay, who's sort of one of the world's experts in applying self-organized criticality and renormalization group to physical systems like earthquakes and cracks in materials, and predicting when the stock market will crash and things like that. And it turns out you can get extreme outliers in these power law systems. And so when you do this stuff and you try to apply it in practice, this is what I mean by saying in theory, practice and theory are the same, and in practice they're different. You can see things like structural outliers. You have to try to remove them. It can affect the fits. So I just want to comment on this to say, I sort of present things in a simple way, but there is some subtlety inside the guts of the tool. And the idea is the tool will do this. I'll give you an example. So this is an example in the tool. If you include these structural outliers, we call them fingers, and we'll finger here, and you try to do the fit, you can get sort of you get a raw fit. This purple line gives you a totally banana result. And so if you take the finger out and you fit it, you get a nice, like 3.849 is a nice fit for this particular layer. I don't remember what model this is from. But this is the kind of thing that the tool does for you when you run it. I can show you sort of how to have these advanced features to figure out what's going on.
Like how does it do it though? Like Like, how does the tool decide what it's?
Well, it removes it, and then it removes it and tries to find the optimal fit to determine whether the fit should or should not include it. Right? It has to search the space and removes them. Right? And so it's actually an advanced feature. You have to turn it on in the tool because it makes the tool like 10 times slower.
Right, but like as far as I understand it, it will be anyway some kind of exploration with some heuristics, maybe.
Right. Yeah. And the reason why it's hard to implement this as a regularizer. People why don't you do a regularizer? It's not so simple, right? It's not so simple. There are other things going on, and so like implementing it, automating all of this takes time because you have to deal with all these sort of funny things. Like you have these kind of fingers, and you have these rank 1 perturbations that occur. So there are funny things you have to deal with, and automating that in a regularizer requires everything to be differentiable. So it's not so easy. So stuff I'm working on, but the theory, generally the theory works, but there are exceptions that you have to know how to deal with them, and we have ideas why it occurs. And again, it's a theory for a theory, right? The Dragon Kings is it really what we think it is, right? So these are things that aren't fully understood, right? Why do these Dragon King outliers occur? They appear. This is another example of something that it's a structural outlier that appears to occur universally in systems that are driven by power law behavior. And there are different mechanistic models, all which lead to the same structural outlier. So we could talk about this in a little more detail, but this is the kind of stuff that when applying the theory, you're sort of taking some ideas in theoretical physics and trying to apply it. You have to there's some subtlety. There are some things some of the as I said, I work informally with UC Berkeley. There's no appointment, there's no funding or anything, just stuff I was doing. Some of the students and former students that are now professors have tried to apply the theory to different things. I'm on some of the papers, not on some of them. One of the things like trying to optimize layer learning rates. So there's papers where you can try to optimize the layer learning rates individually to try to accelerate convergence. This does work. The problem is that it's a massive search space, right? So you have a model if you have DeepSeek and you have 5,000 layers, optimizing the learning rates on all those layers is a non-trivial problem. And so which one should you optimize? You can do LoRa. Turns out you can use the theory to do LoRa, and you can do LoRa in 60%, 80% of the memory of anybody else. So you can do that. You can compress LLMs. So you can take the alphas that come out of the tool. You can transition them to here. You take the alphas, you make them into a score. There's the paper describes how to do this transition to a score. You can put that score into an open source tool, off-the-shelf tool for doing LLM compression. And these tools require that you specify for every layer how much you compress each layer, and you can get a very good compression output. And there's some paper. So there's some papers, but sort of they make these claims. Again, these are student projects or people. So I'm not deeply involved. So take this stuff with a grain of salt. There are sort of ideas that we're trying to flush out. And I point out because getting this stuff to work in production in a tool with real people is a lot of work. You can sort of flush out an idea, but getting it to work consistently across any model is there's a lot of little subtle things that come up. But this is the theory. This is what you can do with it, and there are a lot of other things we're trying to do. We'll stop there and talk a little bit about what the theoretical. I try to start off by motivating you by saying, look, there are a lot of things you can do with the tool. There's a lot of things you can do with the theory. Try the tool out, download it, try it. If you're working on a problem, reach out to me. Would WeightWatcher be suitable to interpret particular weight rows and columns? What do you want to do? We have cases where, so one example would be you can look at the vector entropy. So the vector entropy of the eigenvectors. So the tool will look at the vector entropy of the eigenvectors. This is described in the early JMLR paper. So when you try to look at the rows and columns of the weight matrix, the eigenvectors of the weight matrix do exhibit interesting spectral properties, entropy properties, and they're not necessarily uniform. Some of that is coded up. Some of it we experimented on. We didn't get it all coded. I'm happy to work with you on that to show what you can do with that. And obviously, since we're loading the weight matrix, if you want to look at the individual elements of W, you can do that too. It's like trying to, it depends on what you want to do with it. So what's going on theoretically? I'm just going to kind of go through the theory. As I said, we have two papers on the theory. One is like 60 pages long. The other is 120 pages long, very deep. So, you're looking at it's almost a book on what's going on here. So I try to give talks to answer questions. But it's all the theoretical papers try to lay everything out pedagogically in a way that you don't have to know any physics. It tried to show everything, but it's still hard to describe every detail. So let me sort of explain what's happening. If you have a random, so you go back to basic random matrix theory. Random matrix theory was invented in theoretical physics for nuclear physics. It comes from nuclear physics. It's used to describe the spectra of nuclei. It was then used later. Mathematicians sort of have their own variant. They sort of rederive it using mathematics, and there are some mathematicians who've rederived it, maybe independently, maybe not. But it comes from trying to understand nuclear spectra, and then later for which is when you read my papers, you'll see some of the reference talk about nuclear physics. If I have a random matrix, W, and I draw all the elements of that matrix from some Gaussian distribution or some random distribution that's IID random in some way, then the theory says the spectral density will have a very simple known form. I can plot a histogram of the eigenvalues, where the x-axis now is the value of the eigenvalue, and this is the y-axis, some density, some measure of the density. And I plot and say the matrix is rectangular, so it's rectangular, non-symmetric. So this is called the Marchenko-Pasteur variant of the theory, which is what we want for deep learning. There's another variant called Wigner, which is for real symmetric, but our matrices are non-symmetric. If you plot it, let's say you have the matrix is square. Let's take the blue example. The matrix is square, but it's like 1,000 by 250. So it has an aspect ratio of 4. N is 1,000, M is 250, Q is 4. So we pick Q as 4, and you plot the eigenvalues. You'll see this blue curve. The blue curve is a very specific shape. It's predicted, very easy to predict. It has very crisp edges. There are no eigenvalues less than the below that are less than the left side here. There are no zero eigenvalues. And there are no eigenvalues beyond this very crisp cutoff, except within some fluctuation called the Tracy-Whittem fluctuations. So this is the theory. This is random matrix theory. And the shape of this curve only depends on the shape of the matrix, basically N by M. So as you change the aspect ratio, you make the matrix more rectangular, less rectangular, you get different shapes. So red is the square variant, square non-symmetric. Green is very rectangular. And so we're usually in deep learning, we're somewhere between the red and the blue curves. If you had an LSTM, you'd be you'd be green. The theory doesn't really work for LSTM so well because it just aren't enough eigenvalues. But usually for LLMs, other neural networks, we're somewhere between the red and the blue curves. If you look at the eigenvalue spectrum of a neural network that's well trained, AlexNet, VGG, ResNet, DensNet, BERT, GPT, Plan, most of the layers, 80-20, 80%, at least. Maybe in a llama 75, llamas, nah. They don't look like this at all. They don't fit. If you plot this, the red fit is this is, hold on. It's the blue curve. I plot where is it? Here, I plot the red. This is the actual fit. They all exhibit power law to some extent. And the better the models are trained, the better fit you can get to a power law. So as the models get better, the layers look more and more power law. All the individual layers look more and more power law to some extent. So this is not specific to, this is led us to develop in the original paper called The Theory of Heavy-Tailed Self-Regularization. That as you train a model, there is a self-regularizing property. Now, usually in theory, people thought SGD has a self-regularizing property. This is an empirical observation of how that self-regularizing property is expressed in the layer weight matrices. And what you find is that you might start off, in this case, for example, what I'm doing is you're changing the batch size. This is equivalent to increasing the learning rate. In the old, if you take a simple model and you increase the batch size, it's equivalent to if you decrease the batch size, it's equivalent to increasing the learning rate. Remember, this work was done in 2018, so now people they have ways of training with large batch sizes. But think of this as increasing the learning rate, or during training. As you train a model, the weight matrix starts off, it looks Gaussian random. Over time, these spikes will pull out, which is what you would see in like PCA or traditional random matrix theory or self-organization theory in physics. and you sort of get these spikes which capture some of the information. But obviously there's a lot of information here in the bulk. What happens is as the layers start to become more power law, the information that causes the model to generalize starts to concentrate into the tail, into the power law tail. And it concentrates so much that eventually there is no more information left in the bulk region. All the information that causes the model to generalize ends up in the power law tail. And we have some experiments. This is what the theory predicts. And we have some very simple experiments in our paper, our recent, the 200-page monograph, which show this exactly. So this is the type. This is the old theory, and so we call this sort of these 5 phases of training, and you sort of have this little picture, and you label the phases. And this is just sort of to give you some qualitative idea of what's going on. But basically, the model goes from like random to bulk plus spikes to sort of this bulk decay region where it's half power, so it becomes heavy-tailed. And you can even see a singularity, and the singularity corresponds to rank collapse or very, very large, very, very small exponents. Now, I was asked earlier, where do the bounds come from? So there was a series of work done in the 90s by J.B. Bouchard and Mazard and Potters and Galliucci, who were some theoretical physicists who are now sort of quants. I think Bouchard runs a major quant fund in France. And they had studied this problem in the context of random matrix theory and polymer theory, and had realized that there are different universality classes of random matrix theory. So in normal random matrix theory, everything is Gaussian, right? Everything's Gaussian, everything's easy, you get nice results. It turns out that there's a whole other class of universality classes that were discovered in the physics literature, that what happens when, instead of being Gaussian, you were to draw the elements of the weight matrix from some Pareto distribution. And if you draw the elements of the weight matrix from some Pareto distribution, you get these different universality classes. You get weakly heavy-tailed, moderately or fat-tailed, and very heavy-tailed. And the exponent of the Pareto exponent, of course, can be roughly associated with the power law exponent that you fit. So if the exponent of the Pareto is between 2 and 4, you'll get a power law between, say, 2 and 6. It's not exactly 2 and 4. So alpha will be between 2 and 6 if this is 2 and 4. If this is between 0 and 2, alpha will be less than 2. And you get sort of different bulk structure, and I won't go into too much of this, but basically the idea is that at some point, when you become heavy-tailed enough, you stop being Marchenko-Pasteur and you become power law. So this is known in theoretical physics literature, and sort of the paper sort of describes, highlights this and describes all the various cases. This is where the ranges come from. Yes, where the range comes from, the range comes from this theory. This is why if alpha is less than 2, you get this overfitting, and in fact, there's even a universality class right at mu, which is alpha equals 2. We don't talk about it in the HSR paper, but there's even a little universality class. There's a really special case right at alpha equals 2, which is actually really important for the new theory. Now you can just do this yourself. Quick question: does the heavy-tailed refer to narrower focal cavernous split? Okay, so if you take Wij, and you just go, I can give you a notebook to do this. You just sample it from a Pareto distribution, and you plot the eigenvalues. You'll see when mu is 5, you get the eigenvalues are very tightly. They're in sort of this tight range. When mu is 3, the eigenvalues spread out, and when mu is 1, the eigenvalues really spread out. You get very, very large eigenvalues. And if you do this over and over and over again, and you do it like 100 times, and you try to fit each of these to a power law, you'll see that when the mu exponent's less than 2, you can get a nice power law fit. But as you change the shape of the matrix, there's some scatter, right? But you see that, and as the matrix becomes more and more rectangular, the theory starts to break down, right? So the more square the matrix is, the better the theory works, which is, but you'll see that like here in the case where Q is 1, you'll see that you get the sort of shift. And you can see when mu is above 4 that things look, you don't get the power law fits at all. So you can see these plots. You can do it yourself, and you can see that there's universality classes. And what we do is in the theory, we say we're gonna say we're drawing the eigenvalues. We're drawing the eigenvalues. So we're assuming that Wij, instead of being a Pareto matrix, just that the eigenvalues are power law distributed. So we apply the theory in a way that's a little squirrely because we're assuming that we can apply it to a case of the eigenvalues, even though Wij itself is not power law. So in that case, the theory is more of a phenomenological engineering theory. But it turns out that there's a lot more going on. So in the later work, it turns out you can derive conditions for these that appear to be empirically associated with the power law exponent, which is related to something called renormalization group theory in physics. So you can think of the idea as if you train a model, as you train a model, the model's approaching a fixed point. I don't think this is a big surprise that people might expect as you train a neural network and you'd run back prop over and over that the model maybe approaches some kind of fixed point. What I'm saying is that, and the conjecture is that every individual layer satisfies its own fixed point. Every individual layer has its own fixed point equation. And when the model converges, all the layers converge to their own individual fixed point. And this is sort of the conjecture of the theory. This is sort of the manifold conjecture of the theory that as you train a neural network, you expect all the individual layers to have their own fixed point. Maybe in mixture of experts, it doesn't work in some of the layers, but certainly in the Q and K layers. And so each of these, this theory of training, as you're going through this 5 trade, this is like approaching the fixed point for the layer. So you can write down the fixed point equation. And the fixed point equation for the layer, you can write it down in this paper. I derive the expression for the fixed point, and the fixed point is related to the generalization accuracy of the layer. So you can write down a matrix generalized form of the generalization accuracy of a matrix generalized perceptron. You can write down the generalization. People realize this in theoretical physics. You can write down the generalization accuracy of perceptron. We know how to do this. Make a matrix generalization. You get an equation which looks like the following. You get an integral over a random matrix S. You say, how do you compute the accuracy of a model? Well, like anything, I try to train another model which looks like my model, and I just do this over. I have a teacher, I have a student. I train the student over and over and over to predict the teacher, the student-teacher learning. And if you just measure the distance between the student and teacher predictions, you can get some estimate of the accuracy of the teacher. And so we're kind of running out of time. We can do this in detail, but basically when you do this, you get this equation, which is an integral over a random matrix, which is sort of like the integral over random matrix, times n beta trace HQ, where this represents the accuracy of the layer. So you imagine that every layer in a neural network contributes to the accuracy of the model. And I derive this, in some approximation, like an arm. You get sort of this expression for a Hamiltonian, and you assume that S undergoes a volume preserving or scale invariant transformation. So as S becomes correlated, as W becomes X, as W becomes, as you take X is W, let me see if I can find it here. X is, A is S transpose S. And so the overlap is S transpose T, the overlap between student and teacher. You write this equation down. You assume that the correlations concentrate in the power law tail. You get this expression. You take the large n limit. This condition on the weight matrix that as you take S transpose S or SS transpose, as the correlations concentrate, you get this volume preserving transformation, which is called, this is basically taking one step of Wilson renormalization group. I'll sort of show you, rather than go through all the math, we can go through all the math in detail. I'm going to show you that it actually works. So what you do is you say, I have this new principle of learning. It's a volume preserving transformation. All the generalizing components, all the correlations of a layer concentrate into the tail. We call it an effective correlation structure. This is described by a volume preserving transformation, a measure of a student, S goes to A, or W goes to X. This gives you a condition, which is the trace law condition, meaning that the determinant of the effective matrix is 1. So in other words, if I have a spectral density and I fit the power law tail, and I take the log sum of the eigenvalues, so I take trace log, which is the log determinant of the trace log, so the sum of the log of the eigenvalues, sum of the log of the eigenvalues, that should be 0. So it turns out that basically the empirical evidence I'm going to show you is that when this purple line and this red line are close to each other, this is the delta. So WeightWatcher will compute the power law fit and we'll find this red line. It will try to find the best power law, it will find the best tail which satisfies this condition, and it only looks at the eigenvalues, and it will compute the difference. And what you'll see is that as alpha approaches 2 in the HCSR theory, this condition holds. We train a 3-layer MLP on MNIST. You plot alpha versus that delta. And as you increase the learning rate, you see that the condition holds. This is the renormalization group condition. This is this new principle of ideal learning called Wilson exact renormalization group. You can look at VGG. You can look at ResNet. If you plot alpha versus delta, you'll see that as the alpha approaches 2, this condition tends to hold. Likewise for ResNet. Falcon doesn't have a lot of alphas that are good, so it's sort of there. But for Llama, you do it for Llama, and again, as alpha approaches 2, you see this condition holds. And importantly, if you train a multi-layer perceptron on MINT and you increase the learning rate, and you simply run truncated SVD. So I take the layer, I run truncated SVD, and I compute the test accuracy. If you look at the truncated test error versus the test error, this is the orange. Truncated train error versus the train error, this is the blue. You see that as the alpha approaches 2, the difference between the truncated test error and the test error approaches 0, the train error stays a little high. So in other words, the generalizing components of a layer concentrate in a tail. They concentrate so well that you can throw away everything except the power law tail, and the model still does. So it's a perfect compression. You can do ideal compression of the layer without having to retrain the model. And this is, these are very, these experiments are very easy to run. So you can do this on a very simple experiment. We call this the effective correlation space, because what happens is as the layer is training, as you train the model, you go through this approaching its fixed point, the correlations concentrate in the power law tail. Again, this power law tail we saw at the beginning of the talk, the correlations concentrate to the power law tail. All you need to do is keep these singular components. The power law tail satisfies this condition called the semi-empirical theory of learning, and this trace log condition. So it turns out that the condition that was predicted by HTSR is empirically equivalent to a condition that can be predicted from derived from first principles using some techniques from physics. These conditions appear to hold empirically. They empirically seem to be associated in the ideal case. So in the perfect case, and in the case when it's perfect, which is, you don't get perfect all the time. And very rarely do you see perfect in production. But when it's perfect, all the correlations concentrate in this tail. You can basically throw all these eigenvalues away, and it doesn't matter to the generalization accuracy. That's the predictions of the theory. And again, if anyone wants to stay, I'm happy to stay and go through all the equations to derive everything, but I think it's better to just show predictions. I'll just make a comment that you see the same behavior in real spiking neural networks. So if you look at cultured spiking neural networks, you culture networks, you let them spike, you measure the spatial temporal correlations, you can fit them to a power law, and they exhibit universal properties. This is called the critical brain hypothesis. In physics, it's called self-organized criticality. It was predicted by a physicist named Purbach in a very famous book in the 90s called How Nature Works. Why does anybody know about it? Purbach unfortunately passed away, in his 40s. So the work there are people who kind of follow the work, but he's not around anymore to popularize it. But it turns out that if you look at cultured neurons and you try to fit them to a power law, it turns out as you get larger and more neurons, you can actually fit their spatial temporal coefficients to a power law, or even a truncated power law. The truncated power law corresponds to these dragon kings. So in fact, when I started this project, I didn't start with physics. I actually started using a tool from computational neuroscience to try to understand cultured neurons and applied it to these neural networks, and it turned out to work. And so that's where we are. That's about an hour. I could give you the core dump. Again, the main thing I want you to get away from this is that there's a theory. I'm happy to go through all the math. If anyone wants to do that, I would save you from going through all the equations. But the point is there's a tool. You have a theory. Theory makes predictions. I give you an open source tool. You can test it, try it yourself out, see what you think. Maybe it's useful, maybe it isn't. Let me know. And again, I'm working on things like trying to, we have a SaaS product that we can run very big models for you in the cloud. I'm working on develop regularization techniques so you can accelerate convergence. That's the tool. So I thank you guys for the time, and I'm happy to answer any questions you have.
This was great. Thank you so much. So I have a couple of questions regarding the theory. So I will ask them afterwards. Let's see if anyone has some other questions. And just in case, for the ones who are asking on the chat about recordings and other things, so Cohere posts the recordings on YouTube a few days after the talk happens.
Awesome.
And in our Discord server, I will share later on the resources, the paper and everything, and the slides as well, if Charles shares them. So and also I will share as well the link the invite link to the Discord
That's
of
fantastic. Thank you.
WeightWatcher.
That's fantastic.
Yep. Like you can join the WeightWatcher Discord. So like there are a lot of discussions there, right?
Yeah, I set up writing papers is hard, right? It takes a long time. It's much easier to have a Discord channel and we just talk. That way,
Yep.
you can ask questions, you know what's going on, and again, you can get all the papers there, and that is why I set it up. One of the things I realized I was a grad student, and people don't realize, like, you got to go talk to other scientists. Reading the papers is only like the starting point. You got to go talk to them, figure out what they're really doing, and that was had a huge impact on me in grad school, that you go and talk to people. So what did you actually do here? And then sometimes they can explain something to you that you take you a month to understand. They can explain in 5 minutes. So that's why I have the Discord channel.
Yeah, great. So like perhaps I can read some of the questions that were asked on the chat. Yeah, so let's see. Right, so like Sharad already asked a question about interpreting weight rows and columns, and you kind of answered already regarding the entropy, the vector entropy, right?
Right.
So let me go to the next question. So then the other question says, okay, so why is it harder to train small language model, and where does WeightWatcher comes into play there?
Okay, I think it's harder to train larger models because why does this stuff work at all? Right? Why does neural networks work at all? What happens is that you have a very, very large, complex optimization landscape, and as you're trying to optimize on this loss function. It's a multifractal landscape. We know this, and you get stuck in regions you don't want to get stuck in. And a small model, it's much harder to the landscape is not as convex, so it's shallower. And as the models get larger and larger and larger, the general idea is that the loss landscape becomes more and more convex, and it's easier to get to the bottom. The problem is that you get a large, because you get to the bottom, there's still you're maybe not all the way at the bottom. It's multifractal, and there's probably the model is much larger than it needs to be. So you sort of traded the ability of making the model larger to converge faster. WeightWatcher helps because, again, I'm trying to develop a regularizer that would accelerate the convergence. So if you had a small model, it will regularize very, very quickly. So in other words, it controls the shape of the spectral density and gets you down. And so rather than using something like Atom or Atom W or Muon or something like this, this is a theoretically based tool which tries to get all the layers to converge as quickly as possible. And it does work. Like, we have some early experiments showing the regularizer works, but again, doing anything in production is very, very hard. But that's the idea of the theory, that it tells you, how to get there. So you can adjust. You can also adjust layer learning rates. Another problem with training models is that not every layer needs the same learning rate, because if they converge at different rates, they have to have different learning rates. And this is known, by the way. Like, people use heuristics to create learning rates, where the learning rates at the closer to the labels are sometimes faster than the learning rates near the data. But nobody knows how to set those learning rates ideally. So it's a heuristic. So WeightWatcher would give you the ability to actually adaptively set those learning rates. But again, setting 5,000 learning rates is not an easy optimization problem. So that's where we are with the theory.
Right. So like also, as far as I see in the mathematical derivation for the Wilson renormalization group, you do take a limit at the weight going to infinity, at the size of the matrix.
Well, it's a Largian limit. Yeah. You take the Largian. This is in physics. This is called, to find it. In physics, this is called a mean field theory. So the theory is So this is standard thing in physics. You write down a mean field theory. You take a saddle point operation, and evaluate the Largian. This is this is sort of like bread and butter physics stuff. That's right. But that's just, it's the thermodynamic limit. So you're evaluating the model in the thermodynamic limit, which is in this case the Largian limit. And in the paper, I will talk about.
Yeah, like for me, it's still counterintuitive whenever I see it, because like with this limit, you technically don't learn any features. So it's
that's the NTK limit. That's a different limit, right? This is what Greg Yang has pointed out in his work, is that the NTK limit is the wrong limit for learning. So he's argued that in his theory, if you guys know anything about NTK, Greg Yang's work on tensor programs, no, you're in a completely different limit. So, and Michael Money and I have a talk on this from 2015. We have a paper from 2015 where we describe, obviously a different limit. You have to take a different limit. You have N and M. right? So in my theory, you take large N, but M also becomes continuous, right? So you have to, this is something where, that is, the density becomes continuous in the large N limit. So we're bounded. So it's a different limit, and you're in the thermodynamic case. So it's very, very different. So the NTK stuff doesn't really apply. Yeah. By the way, it's well known in statistical physics that if you look at like small models, you can apply mean field theory to, basically you take the saddle point approximation of an integral, and then this is what replica theory is all about. It's like you apply a saddle point approximation, you take the margin limit, and then you go and look at finite size samples. Theory works very well. It works very well for finite size systems. This was work done in the late 80s, early 90s. Vlad has a question.
Yes. Hello. Thank you, Charles. It's really fascinating what we hear here. I mean, I'm feeling that I'm too stupid for this conversation and in this presentation because I'm definitely not a data science
and smart enough
not
not to spend 10 years to do this.
But it's definitely super interesting. I mean, out of my position where I am just starting with the AI, I have basic questions definitely. And just a question here regarding the open source model that you're working with, and that the WeightWatcher is stepping in there. Is it possible theoretically and practically to use WeightWatcher and all the existing open source models to train themselves in the setup where you have them overtrained model trained their not so trained models, and can one model actually expedite the correct direction of the learning of the model on the way that you desire? Is that make sense? The question.
No, it's just teacher learning or curriculum learning. People do this all the time, right?
Okay.
They take a good model and they use it to predict labels or help train a smaller model.
Okay. All right.
I mean, what I'm doing, we're basically trying to monitor the weight matrix. So the idea is that, I mean, when I get to understand, I try to build a theory. I don't have money to train models, right? And I don't want to analyze giant matrices with 10 billion data points. So I said, what can I do theoretically that doesn't require me training any models or accessing any data? Well, I'll do some theory on the layers. It turns out it works. So, certainly you can try to use, people use curriculum learning or student-teacher learning to try to predict, given, how do you correct the model? Did it make the correct predictions? Like in reinforcement learning, right? The thing would make, you can imagine a model making a bunch of predictions, and then another model would look at, this is right, this is wrong, and you go back. So people are trying to do distillation. It's a distillation technique, for example, to train a small model using a large model. And you use WeightWatcher to monitor the weight matrices to make sure the distillation process is optimal.
And in general, I mean, if you're talking about an application of AI model for specific use, like for enhancing some performance of some SaaS, edtech or some martech or something, basically there is no particular use for a large language model because one, it's too expensive to train and maintain, and two, it's lying so much. So it's actually no use for a big expanded large language model, right?
Well, people are trying to do things without these things make stuff up. So, you're going to use the thing. If you try to use these models in an environment where the predictions have to be exact, you got a problem, right? Look, we used to work in things like ad click prediction, or, recommender systems for search. It doesn't matter if the model makes mistakes because the user is interacting with it. So the user understands that, when I search for something and I maybe I don't click on the first item, I click on the fifth item. So the model didn't predict exactly what you want. If I had a client years ago that wanted me to make a tool to predict the ingredient, to label the ingredients in a recipe. Label the ingredient, extract the ingredients in a recipe from some random blog anywhere on the internet, right? And it had like 95% accuracy, and the product manager was in shock. He goes, well, this thing, it has errors all the time. Yeah, it's 95% accurate. Do you understand what that means? It means it's going to miss 1 out of 20. Okay, so if you have if your average recipe has 10 ingredients or 20, and it's going to miss a lot of them. So you have to expect this. Like, what did you expect it was going to do? They don't understand what 95% accuracy means. He thought 95% accuracy means if I give you 100 recipes, it'll miss 5 of them. That's not what it misses. You're asking to extract. It misses It misses 5 ingredients, right? Not 5. So it's this. I'm trying to give you the ideas that you're working in a client in a production environment with customers. You have to be clear about what it means to have an error. So there are cases where the model will make an error. It doesn't matter. There's no cost to the error, right? There are other cases where the model makes an error. There's a huge cost. And so you have to manage. And so when I work with clients as a consultant or I'm managing projects, you have to be careful with this. You know, like, why would you put something in production? Like, I would never let this thing have root access to my machine.
Yeah. But as long as the model can train itself and improve itself, then it's fine, right? I mean, if you just fine with 5% accuracy, right, then it's improving.
In this particular case, it turned out it was easy to fix because it was something you were giving to the user for their blog, so they could just make the correction themselves. Oh, it made a mistake. I'll fix it. It wasn't a big deal. But from a product perspective, it was a misunderstanding of, what does it mean to have accuracy? All this was like an SVM. All models make mistakes, so you have to manage the error.
And just a quick question, Charles, regarding the production and development environment, is there any difference in how a model behaves in general and in these different environments?
Well, I mean, look, why did I build WeightWatcher? I've tried to build machine learning products for clients for 20 years. And the biggest difference I find between doing machine learning and AI versus other types of software engineering is that there's no way to debug it. You have to debug everything in production because the data is in production. And there's no way, no one has proper replicated data in the dev environment. So it's just, you can't, like when we built the ingredient recipe, the ingredient extractor, I actually built a regression system that would test it like we had all the data in the test environment. So you could test the thing before it went into production. But for the most part, and that took like 3 months to build a testing system. When you deal usually with clients, they just put things in production and it breaks constantly. And the idea of WeightWatcher is that, I can monitor the model in production to see if the data pipeline if the data pipeline goes crazy, you would see that the model weights would go crazy. And and so that was sort of like my original motivation was like, that's
makes total sense. So it's basically like a battlefield testing during the battle,
right? That's why I built it. And I did, and so now of course people are doing prompt engineering. So who knows how to evaluate prompts in production, right? Like, how do you evaluate a hallucination in production? They're very hard. But if you're like fine-tuning models, yeah, you would like, I've built fine-tuning systems and training systems for years, and people put things into production and there's no way to get, and the problems are always the data pipelines fail. And they fail in production. They never fail in test. Test is easy. And this is very different than traditional software engineering where you have code, you bring it to your laptop, you debug it, and you deploy it. It's a completely different mindset. And it causes huge problems. I see this. This is not really so much WeightWatcher as much as my consulting practice. But I see this everywhere. Right? This is everywhere. It's like, well, it's, the code runs, but it's nonsense.
Right.
Question. You're asking, but what about the interactions between layers?
Right.
Okay.
Let me actually elaborate a little bit. So, like, it's not. So it depends on what you call a layer, right? So like, as far as I understand, you call a layer anything that is linear, right? Like anything that is learnable. So if you apply a query projection, that's a layer. If you apply a vector projection, like with another matrix, it's another layer, and then they interact, right? So yeah.
Right.
So like what does the theory predict anything about it?
Well, we don't predict it, right? So WeightWatcher can compute if you use the term intra. It will compute the intra layers. There are some people who claim that inside, I haven't looked at this in detail. We can look at this. So people who claim that like inside a LLM, that the KQ matrix, if you multiply it together, becomes low rank. It almost becomes like a rank 1 system. I don't know. I mean, we see that their power law, maybe when they interact, they become much lower rank, and it's something we haven't looked at yet. It's just some coding issues. Theoretically, the issue is that typically in the layers, when you look at the layers between like attention heads or like an MLP, you would have a ReLU between the two layers, and this acts as a kind of whitening. process. It randomizes the interaction. It dampens the interaction between layers. You bet, Vlad. It dampens the interactions. And so in the theory, the argument is that, well, we're at the fixed point of renormalization group. And when you're at the critical point, in the critical point in a renormalization group, the correlations become so large between the system that they dominate over any fluctuations. So this is why when you say you're taking one step exact renormalization group, you're literally saying I'm ignoring interactions between even coupling terms. Like even in the theory, there are coupling terms. So if you look at the theoretical derivation, there are these coupling terms that arise. So the theory sort of looks, you get this couplings, and you have to basically assume that you write down this integral. I find it here. You write down the integral, and there are couplings between these terms in the exponential. And what the theory says is, we're going to assume that since we don't describe it exactly in the paper, but using ideas from renormalization group theory, because we just sort of call this the independent fluctuationist approximation. We assume that this integral can be factored, and the bracket means integral, right? The bracket means take average. So we assume that this integral can be converted into this integral. So we can factor it. So again, we have the bracket means d mu of a. So the bracket means take average, and we assume that this average over these two terms can be factored into averages over two terms. Then we take a point estimate of the term on the right. And the idea is that now you've ignored even internal fluctuations. Like this is like, and then additionally, you ignore fluctuations between the layers. Now there may be something going on with the K and Q layers inside an attention model, and you're on the network. We try to figure it out. Like just time, right? It just takes time to analyze all this stuff. But this is what the theory is doing. And normally, when you do like theoretical physics, you have to deal with this thing directly. So you get basically what they call sometimes like vertex interactions that you have to deal with. So in a real theory, like if you're really a physicist and you're studying some model, like you would actually deal with you would get this, and then you would get additional coupling terms. Like this would be expanded into like terms of couplings, and there'd be it'd be like some sort of complicated perturbative expansion where you would deal with these higher order fluctuations. I can't deal with any of that. I'm doing this in my spare time. I don't have time. I can't work out all that theory, but that's what we do. And that's the argument that's why you really, as a regularizer, you're trying to drive the system to these fixed points. So the regularizer is just trying to pull you down to the exact fixed point. So hopefully these interactions between layers wouldn't be so important. But we don't know, right? It requires more analysis.
Right. So, Mayan, do you have a question? Because or otherwise I can ask my next question.
So I would like to know about if we go down the rabbit hole of MOEs, for example, if we look at the DeepSeek MOEs, and we have the router where we have the shared expert as well as the standalone expert that takes in the tokens that are routed. So can we dig deeper into that stuff with I think so we can with the tools that you guys have, but my query was, has anybody delved deeper into that sort of stuff with the mixture of experts and the innovations and the enhancement that are happening nowadays?
Right. So here's from the WeightWatcher. You got to join the WeightWatcher Discord channel to get this stuff. So this is an analysis of DeepSeek. So the thing about DeepSeek is that it doesn't have. They mixed up they merged some of the weight matrices, so you can't separate the K and the KQ and V are mixed up. So you get this sort of KVA projection. So you get this weird purple line. So as I said, recall before that the K and the Qs in Llama are very tightly correlated, and the V is all over the place. Well, if you mix them up, you can't analyze them anymore. They're all over the place. So you see this sort of weird thing where you have. This is an analysis. So let's see so I can see more carefully. There we go. So this is DeepSeek. So brown is the KVB projection. Purple is the KVA projection with the MQA. So this weird thing that they did. So, it's all over the place, right? On the other hand, if you look at the gate, the other layers are like here. This green one is QB projection, and this grayer one is QA projection. They're down here in the safe range. So, but this KVA projection with the MQA, whatever that is, that looks like the V projection in Llama. And here's the KVP. So, they're mixed. They're somehow combining things in a way that makes it a little harder to analyze. But this is what DeepSeek looks like. So you can look at DeepSeek. We have DeepSeek. We have Llama. You've seen the awesome.
Yeah.
I lost
Yeah,
it. I
that's
pressed the wrong button. So yeah, you can look at it. But again, the structure of DeepSeek is different than. So this is again. Here's solar. Here's solar. And again, when you have K and Q, green and purple, you see that the green and purple are. Here's green. Right, green is easier to follow. It's in the safe range, although it's much larger than Llama. Llama actually has the tightest range. But in terms of these mixture of experts, there's one we have muon. We did muon at some point. Gemma, Llama, DeepSeek. I did muon. Mistral. Here's Mistral. Right, Mistral has the same behavior again. What is that purple one? The purple is the V. So Mistral, again, in Mistral, you have the K is green and the Q is purple. And so you see the green is here. It's not, again, Llama's tighter, but it still works. I'm seeing, but the one you really care about, if you want to look at mixture of experts, is muon. Yeah, I don't have it here. Sorry. You can look at what.
Yeah. What
you see
I will do is I will join the Discord and I will converse with you guys. I'm in the process of writing a paper, and these kind of expeditions will be helpful in trying to
So one of the things we saw with muon is that muon tends to the muon optimizer for MOE. So someone released this, and it tends to create, and they have to we want to create layers that have high entropy. Well, it turns out in muon, it's mostly all MOE. So you have all these layers that are very, very high entropy. But then if you go and look at the K and Q layers, they're just like Llama. So it's what they're saying. They themselves didn't look at it. So we can somewhere I have the muon results, and if not, we can look them up again. I have them somewhere. But that's the kind of stuff you see.
Yeah, and plus, I was also wondering from a theoretical perspective, since you mentioned Greg Yang's work. So I was also kind of looking at MOEs from that, and if we have that kind of analysis for the different routers and stuff. So yeah, we can discuss it on Discord.
The main difference between what Greg Yang is doing, what I'm doing is, Greg Yang he's saying, let's say you've optimized all the hyperparameters. How do we scale them up to a big model? How do you make the model wider, right? And what I'm saying is that how do you optimize hyperparameters? So I'm saying take a small model. How do you find the optimal case? I don't get. No one pays me to train giant models, so I don't bother scaling them up. But that's the key difference between what he's doing and what I'm doing. And theoretically, what I'm doing is very he's using more traditional random matrix theory type analysis, and I'm using really techniques from theoretical physics.
Oh, thanks.
Okay, so thank you so much for the talk. It was amazing. I will ask some kind of non very scientific question. It's more about do you think there should be some kind of reconciliation or more like internal work collaboration between the statistical physics people doing stuff in machine learning and the people from example from Anthropic that are doing mechanistic interpretability?
The statistical physics guys, look, they're not doing what I'm doing. I'm doing semi-empirical theory. So my theory allows you to describe the properties of the model in terms of its empirical observables, right? The key idea of the theory is that in the final result is that the free energy or the generating function for the theory can be described in terms of this layer. I derive an expression for the layer quality metric, which is in terms of the free cumulant expansion of the spectral density. This is totally unheard of in statistical mechanics, right? This idea comes from quantum chemistry, and so they don't think this way. Their interest is in give me a simple model, and I will expand the model in some analytic theory, right? So they're trying to, they're trying to do, they're trying to solve this problem. How do I do all the couplings? So let's assume H is very simple. It's an Ising model. How do I deal with all these couplings? So there are papers now with people doing stuff similar to this. I saw a paper recently that had sort of this sort of same formulation of the HCIs, the integrals, and the RG stuff, but it doesn't lead to a regularizer, right? It doesn't lead to anything you can do practically. And it's because of their mindset is, I want to write papers, I want to do analogies. They don't think in terms of, how do I build tools for people? And how do I build tools and give those tools to people that will have impact on what they're doing? It's a different mentality. And it's difficult to get them to accept like what I'm doing. In a sense, it's like they know the math, but the setup is different, right? Like the intent is different. So I think it's fine I worked with a guy who was a stat physics guy to develop a lot of this stuff. He's at Microsoft now doing, he's bored out of his mind, right? But it's tough to, it's yes and no, right? They have to be aligned with actually making results that are related to, and statistical physics people are not always connected to experiment. If you look at John Jumper, my graduate peer, right, who just won the Nobel Prize, his early work was statistical physics. It was, his early protein folding work was statistical physics combined with machine learning to do protein dynamics. That was his thesis work. And I remember when he did it, and Carl telling me, the advisor, like, we don't even know we're going to publish this because it's so different from what everybody else does. So you'd have to convince them to do things in a way that's useful, as opposed to doing sort of analogies or post hoc analysis. So I'm not against it, but dealing with these guys, they live in their own universe, right?
Okay, I understand.
You have to kind of start from scratch, right?
Right. So no more questions from my side. The only thing left is that I will share all the links in the Discord community that we have at Cohere, and yeah, hopefully you'll have more interactions in your Discord coming from us.
Right. I'll just answer the question again. Like, part of the reason I wrote this paper is to motivate younger people to think in this way, right? So like the old guys, they think the way they're going to think. Part of the statistical physics stuff I'm doing is to tell younger people who know statistical physics, hey, look, you can do it this way too. And maybe that will motivate some people. So in that sense, yeah, I think we could get them involved if they're interested in doing things that actually drive deep learning forward. That was helpful. Maybe. I don't want to seem negative. All right. Hey, thanks again. I really appreciate the time, and I look forward to seeing the video online.
Yeah, same. See you. I'll talk to you later. Bye.
Right. And thanks for the great questions. All right.
Bye. Take care.
Goodbye.